Good afternoon. So let's come back to the natural language processing class. So this week, let's discuss representation. So it's a more complicated week compared to simple counting. And this is where we are, right? So week 2, we reviewed the basics about building a model. And week 3, we built very simple models, like by counting. So they are generative models, probabilistic models. So this week, we will shift to a kind of non-probabilistic models called discriminative models. And these models are built upon a representation vector. Okay, so this is the first time we talk about representation, which is very important for NLP. Okay, so we have the following goals for this week. So the first is to learn feature vector representation. And then we can discuss what we can do using these vectors. And then we will discuss two of the discriminative classifiers which you have learned in your machine learning class, support vector machines and perceptrons. Okay, but in the context of feature vectors. So we will learn how to differentiate discriminative models and generative models. So this is the outline. So we will first look at representation and clustering and classification using the representations. Okay, these are binary classifiers. And then we'll move on to multi-class classification, right? So I don't know if you learned how to use SVM and perceptrons to do multi-class classification, but they are naturally binary classifiers. And finally, we will discuss features, okay? A central idea for the linear NLP models on representation. And we will see that the representation will affect your model's capability, okay? In both training and testing scenarios. All right, so those are the 3 parts for today. So the first part, let's look at representation. So to this end, let's first review naive Bayes classifier. You know, we built this classifier last week, which makes use of 2 types of patterns, right? So one type of parameter is PCE. So how likely is your class label, right, beforehand? So if you're given a random document, how likely it is positive or how likely it is technical news. The second is the association between a word and a class label. So this is the very important pattern we want to use, right? So if you see a document with a lot of CEO, stock, and market, maybe this is a finance news, right? So how do you get that idea? It's because, like, given finance news, right, the probability of CEO is high. So this is one of the parameters you use, right? And similarly, if you have a lot of things like club, fans, this is more likely to be a sports news, right? So you make use of the association between words and class labels to make decisions in your naive Bayes classifier, right? Which means that words are actually indicative of the semantic meaning of your document. So if you put your naive Bayes classifier into this form, okay? So you know naive Bayes classifier is the sum of a log pw given c plus log pc, right? So you can put your document, okay, into a vector like this, a representation vector. So this vector has vocabulary size, okay? And each element in the vector represent how many times a vocabulary word exists in the document, okay? So if like fence, the word fence exists in a document 5 times, right? CEO 0 times. You put the document into this vector, okay? And then you use it to dot product another vector which contains the model parameters PWC, okay? The first vocabulary word, second vocabulary word, until the last vocabulary word, all right? Dot product end up with the sum, right? The sum of every word, okay, in a document, it's count times log PWC. It's basically the PWC part of your naive Bayes model. You want to make the sum of all log PWC, right, for every word in the document. All right. So, and then you have another term, which is log PC, right? I just added here. So it means what? It means that in addition to the knowledge of the class label, the frequency of the class label, the remaining part, okay, the PW given C part can be decomposed into a representation of the document, right? Dot product, all these probabilities you have learned, right? So let's look at the representation of the document. All right. So it's a vector, right? It's in a high dimensional space. So if you have a lot of CEOs, it will reside, okay, on the CEO coordinate, the coordinate that corresponds to the word CEO, right? If you have a lot of fans existing in the document, then the document will reside in an area where the fans coordinate is high, right? So, so basically when you map the document into a vector representation, you put the document into a high dimensional space, okay? So each coordinate, each dimension corresponds to a word, right? So where the document stays depends on how many times each word exists in the document. All right, so this is like a count-based vector representation of the document. And you can think of naive Bayes as making classification based on the document representation and its log p parameters. So this is a first observation. So let's make a formal view, right? So you want to turn a document into a vector. The vector has vocabulary size. And then your vector in general has f1, f2, dot, 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 until fn. Fv, v size, right? So, and each element in this document representation reflects how important a particular word is to the document. Okay, it also reflects the document meaning. So, in the simplest case, we can fill the f elements with the count of every word in the document, as we did earlier. Right, so in the last equation, you see the vector representation of D will be the count of word 1 in the vocabulary, word 2 in the vocabulary, until word V in the vocabulary, last word in the vocabulary. And here I give you another example, right? So suppose that we have 4 documents. One is Tim bought a book. One is Tim reading a book. One is I know Tim. The fourth one is I saw a boy reading a book, right? How do you map these 4 sentences or document into vectors? So basically, you map every document into a column vector like that, column vector, okay? So these vectors are vocabulary size long, and each row corresponds to a vocabulary word, Okay, so basically you arrange the whole vocabulary into a column. Right. The first word in the vocabulary might be right? The second word in the vocabulary might be right? Something like that. And then you map documents into column vectors by counting each vocabulary word in document. So for D1, right? So we have a count of 1, right? And Tim will have a count 1, and bought and book, right? And period. So in addition to these 5 words existing in the document, all the other columns are zeros, right? So this is a very sparse vector. Remember, sparsity means the number of zeros in a set of items. Okay, so it's a sparse vector. So similarly, if you map, I saw a boy reading a book, the first row will have a content of 2, because the word exists in the document twice, right? And for the other words, they're just the counts, right? Okay. Now, so as I said, so each dimension in this vector will represent how important the word is to the document. But then you realize, wow, the words and the and of, these words, they don't carry a lot of meaning, but they are very frequent almost in every document, right? So if our document representation vector contains a lot of these words, you will have some troubles, right? Because all the documents will live in similar areas in the vector space. Because these features are very salient, and they are not representative of the meaning, okay? So people, the researchers, they realize this, okay, when they work on the representation of document, and they name these words stop words, okay? And here in this slide, I showed you a set of stop words, like the, on, with, etc., and period. You don't want these words to affect your document representation. So how can you do that? One brute force way is to say, okay, I know a list of words that are not so representative. So I will just delete them from the vocabulary, okay? So then your document representation will be a smaller vector, okay? Not that smaller, but smaller without stop words, okay? But you have to first assemble a set of stop words, right? And then you delete them from the vocabulary. So this is like making hard rules, but how can you make sure that you include all the stop words, right? And how do you make sure that your stop word list fits your data? Maybe some of the words you think are stop words are actually very indicative. For example, on, right? On the table, it has some meaning, right? How do you know that these words are really not so important? So as we discussed in week 1, right? Instead of using hard rules, you can use sort of statistics, right? To solve the problem. How can you think about some statistics to decide which words are frequent and not important? So people developed this a document frequency concept. What is a document frequency? Document frequency means in how many documents or in what proportion of a document set, okay, does the word exist, right? So if you have 10,000 documents, okay, in a document set, and a word the, right, exists in every document, then you have a very high document frequency. But out of 10,000 documents, your CEO, the word CEO only exists in maybe 5,000, right? So it has a low document frequency. So CEO is more indicative than the, right? So with this idea, right? So they develop a representation of the vocabulary words without hard rules, without deleting word, but they use a term frequency divided by document frequency to represent every word. So the term frequency is basically how frequent is a word in this document, okay? And document frequency is like how frequent is a word among all documents. So let me give you a formal definition. So the term frequency and document frequency vector is called the TF-IDF vector. Why is TF-IDF? TF is term frequency. IDF is called inverted document frequency. So if you think about term frequency divided by document frequency, right? So you can also think of term frequency times 1 over document frequency. That's called IDF, inverted document frequency. Okay. So how do you define term frequency? It's the relative frequency of a word in a document, right? So basically it's how many times does a word exist in a document divided by the total number of words in a document, right? Term frequency. All right, document frequency is what I just introduced. And then you can use TF divided by DF to represent every word, all right? So that will remove the influence of stop words by using statistical information. And then people realize when the set of document is huge, okay, your DF might overweigh your TF. That's what you don't want, right? And people develop some engineering tricks to reduce the influence of DF. For example, they take the logarithm of DF, okay, as the document frequency. So that will highlight the term frequency while also consider the document frequency. And if you do that, let's go back to the 4 documents we discussed earlier. You realize the influence of will become relatively reduced, okay, by using TF divided by DF. And the influence of words like Tim and boy will be relatively stronger, okay, after you do the DF normalization. Still column vectors, right? All right, so what did we learn within the last few minutes? Okay, so we learned how to turn a document into a vector, okay? And basically, every dimension in the vector space corresponds to a word in the vocabulary. And we learned 2 ways to turn a document into a vector, right? One way is just counting. One way is using TF-IDF to balance the document frequency and the word frequency. Okay. Now, when we have a vector representation of the document, then we can build mathematical models on them, right? So, and the whole theme of this week is how do you play with vector representations of document, okay? So, first thing first, when we map document into a vector space, of course, mathematical calculation will be feasible. And we can immediately draw the correlation between documents. As I mentioned to you earlier, the sport document, they will live together, right? They will be very similar to each other. The finance document, they will be similar to each other. And how do you measure this similarity? So one way is to measure the Euclidean distance between the documents, you know, right? So you take the difference between 2 vectors, right? And you measure the norm of the difference. That's the distance in the vector space. So another measure of similarity is like the angle between the 2 documents, the direction, right? So why do you need angle between the documents? Sometimes it's very useful. For example, if you copy and paste a document twice, you know, I like NLP, I like NLP. That will be a different document, right? So the new vector will be twice as far from the original point, okay? Compared to the original vector. So they have a distance. But actually they mean the same thing, right? So their angle is the same. Right? So you care about the angle and you care about the distance. So the distance measure is like this. I call it Euclidean distance. All right, so you've all learned this vector space geometry. Let's just review that. And how do you measure the angle? The angle is the cosine difference, right? So two-vector cosine difference is what's written in the slide, and you have all learned that, right? I'll just take a quick review of that. Those are the distance issues. When you have a distance measure, then an important task you can do is to like cluster documents, right? Well, I have a group of documents, you know. I want to put them into different, you know, themes, you know. Maybe one group of documents are sports news, another group are finance news, another is political news. So you have a set of documents in the vector space, right? I reduce the dimensionality to two-dimensional to illustrate that. But actually, it's very high-dimensional, right? You can do clustering. You want to put close vectors together into a cluster. So that's the basic idea. Now, for humans, it's very easy, right? I just observe. They live together. It's a cluster. They live together. It's a cluster. But for algorithms, it turns out to be non-trivial, okay? So because all that algorithms know are vectors, you know, they don't have a global picture of who is who, where is everyone, okay? So people have devised the different algorithms to do that clustering. The first thing an algorithm struggle with is how many clusters there are actually, right? So for us, we can look at, just like when we look at a picture of dots, right? We can see this is a group, this is a group, but it turns out that for algorithms, this is challenging. And second, like, how do you assign like dots to clusters, right? If you think about it. All I know are vectors. I can iterate through these vectors, but I don't have an idea, right, who will belong together. Right? So these are the two challenges. So, but I will introduce just a very simple algorithm to this end. It is called k-means clustering. So to the two challenge, right? K-means provides you simple solutions. The first thing is, I don't know how many clusters there are. The k-means says, okay, you specify how many clusters there are. Okay, I take it as input, right? So k-means, okay, if 2 means, you mean you cluster things into 2 groups. 3 means, you cluster things into 3 groups. Now the number of clusters is solved. Even if it is solved, then I don't know how to group these vectors together, right? How do I group them together? So k-means takes a very simple approach again. So basically, it says, if you know the cluster center, right? So if you tell me what are the centers of the clusters, then I can iterate through all the vectors and make assignment, you know. Because I'll just look at how close I am to every center, right? I'll choose the closest center to assign myself. That'll be easy, right? That's just a for loop, right? Right? For every vector in the document set, right? For every center, I calculate the distance to that center, and I choose the closest center to assign myself. That's it, right? So if you know the cluster center, then assignment to cluster is easy. But you don't know that, right? So k-means is an iterative algorithm, you know. So first, it will select, okay, k random vectors from the input as the initial centers, right? Then it can make cluster assignments, right? After they make cluster assignments, they can recalculate the cluster centers by averaging every vector in the cluster, right? So the cluster centers are updated, and then you reassign every vector by reconsidering all the cluster centers. So this is an iterative algorithm. So this is pseudocode, okay? So you initialize the set of cluster centers, you know, you specify k, so you choose k random vectors as cluster centers, and you repeat assigning vectors to clusters and calculating new cluster centers until they stabilize, they don't change anymore. And you got the clusters, okay? This is a simple algorithm. My purpose is not to make you very fluent to the algorithm, but to show you, okay, you can cluster vectors, right? As long as you get vector space distances. You want to know more theory, right? A lot of students, you ask, wow, you told me an iterative algorithm, but how do you guarantee, okay, they will cluster as human intuition? Why will they converge? Why won't they just like oscillate, you know? Right? Will they converge? And when they converge, do they converge to the intuitive clusters? All these theories, okay, are written in chapter 6 of the first edition of the book. Okay, if you're interested, you can look at them. Okay, we have theoretical guarantee, but the convergence depends on how you make random initial assignments. If you don't choose correct or reasonable initial cluster centers, then maybe your algorithm will not converge to good clusters. All right? So this is how the algorithm clusters the 4 documents we talked about in the very beginning. You know, the 4 documents are like this. If you take 2 means clustering, it will group the first 3 documents together and the last document as another cluster. It makes sense, right? Because the first 3 documents are all about books, you know, and the last document is about me and Tim. Right? But if you do 3 means clustering, then the first 2 documents will be 1 cluster. The third and fourth will be 2 more clusters. That also makes sense, you know, because the first 2 documents are about Tim and book. The third document is about boy and book. And the last document is about me and Tim. Okay? So it all makes sense. It means that, okay, so the document representations are cool, right? You can know the meaning of every document. But then in machine learning, you learn classification, which is different from clustering. So what's the difference? Okay, suppose that in my mailbox, I have 2 types of emails. One is work and one is leisure. You know, leisure email also sent to my Gmail. Work email also sent to my Gmail. But I have another criteria. It's travel and non-travel emails. You know, many of the emails are non-travel emails, but a lot of emails are about itinerary travels. I go to conferences, I go to seminars, and I go to vacations. All right. So I have both the travel and non-travel emails. I have both work and leisure emails. It's a complicated system, right? So when I do 2 means clustering, how will my algorithm cluster my emails, right? Will it cluster to work and leisure, or will it cluster them to travel and non-travel, or neither of the 2? I don't know, right? It all depends on my vector representation. So it's like this. I have some emails in the vector space. And maybe naturally they are grouped into cluster 1 and cluster 2 like this, okay? But actually, what I want is to differentiate my travel emails and non-travel emails, okay? Like, I want to differentiate my travel emails and non-travel emails. But they might group my emails into 2 groups according to the distances. So clustering is not in control. Okay, can't control how the documents are clustered. But how can I control, like, how do I classify things? The idea is, okay, I don't care about how far these documents are, but if I can draw a line, you know, a line in a high dimensional space, this is called a hyperplane, right? So if I can draw a hyperplane to cut my emails, then I don't really care about the natural clusters. I know this is what I want, right? So this hyperplane is my classifier, right? it's still based on the representation of documents, right? In a high dimensional space. But if I can find a hyperplane to separate them, then I have control, right? If I want this work and leisure, I do this, cut, okay? If I want travel, non-travel, maybe I do this cut, okay? So if I have a hyperplane, I can control. That's classification, not clustering, right? So we learned the naive Bayes classifier. So how does naive Bayes classifier classify, do the cut, right? What's the mechanism? All right, you have the document representation, which is a vector, right? And how do you do the control? You have some parameters, These parameters are trained, right? So the parameters are log W given C. And this parameter vector actually defines a hyperplane. You can think about it, okay, like that. So you train every parameter, so sort of it serves as defining the hyperplane, how to cut my vector space, okay, it's here, right? Without the parameters, you can only do clustering. But with parameters, you can do classification. So that's the basic idea between classification and clustering, right? Okay, you use parameters to control how to cut, right? Why don't we review two algorithms that use parameters to cut vector spaces? Let's look at the first one, support vector machine. Okay, you must have learned support vector machine in your machine learning class. Okay, but now let's look at from a NLP perspective. Okay, I just want to define a hyperplane, to cut my vector space. All right, according to my training data. Let's look at the parameterization later. Okay, but the idea is suppose I have a lot of blue dots and red dots as my training data. Okay, in a vector space. These are documents. And I know how to classify them because I color them blue and red. That's my labeling, right? In week 2, I learned. I tag that as positive, tag that as negative. I just want to separate them. So all I need to do is to, use some parameters to represent the hyperplane, okay? The hyperplane will separate the two things, right? And then if we are given a new document, I also map that document into the vector space. If it's on the upper side of my hyperplane, it's work. It's on the lower side, it's leisure. That's what I want to do, right? So that's the intuition. We're still playing with representation vectors. But you first have to solve a problem. Are your vector representations separable? Okay, so maybe in the vector space there's no hyperplane that can cut the two types. Okay, and maybe there are. So now we are assuming that there are. Okay, so this is called what? So this is called linearly separable. So if your training data are linearly separable, which means we can differentiate the two sort of vectors by a hyperplane, then you can define a linear model, okay, to cut the two. So, and linear models, I will introduce SVM and perceptron. These are two, okay, which you also learn. So SVM is very simple. It just works in the vector space, How do you define a hyperplane in a vector space? This is also geometry knowledge. Every one of you knows, okay? So a vector space, the hyperplane is omega v plus b equals 0. Okay, that's a hyperplane, right? So x is your input vector, v is your input vector. Omega, is the direction vector, right? It's orthogonal. Omega is orthogonal to your hyperplane, right? This vector, it decides, the orientation of your hyperplane, right? So b is the bias, right? It decides how to shift, up or down. So omega v plus b equals 0. So for all the vectors that are on the hyperplane, omega v plus b equals 0, right? For all the vectors on one side of the hyperplane, it's above 0, right? For all the vectors on the other side of the hyperplane, it's below 0. This is what you learn, right? So I use omega v plus b, okay, as my parameterization. We can separate dots in a vector space, okay? But hold on, I will refine that parameterization later. But so far, let's just take the intuition. Now you know how to parameterize your model, and the next thing, you know, the 3 steps in building a model, the last step is to train it, right? What are the model parameters? Omega and b are my model parameters. I want to find omega and b values, okay, to separate my training data. So that's the goal. Okay, how do I find them? Well, different omega and b defines different hyperplanes, you know? And then, you know, in your training data, there are 2 types of things, right? The black dots and the white dots in a high dimensional space. And you want to define a hyperplane to separate them. And you find, wow, there are many hyperplanes that can separate them, maybe, right? There are many of them that can separate them. So, you know, the red line can separate them, right? The vertical blue line can separate them, right? Right? The tilted blue line can separate them? No, right? So you want to choose from those that can separate the dots, right? So do you want to choose the red one or the blue one? You want to choose the red one because the blue one is too close to some of the training samples, right? So if you see new training samples, you're not sure which side. You want to choose the safe one. So how do I define the safe one then? Okay, the safe one is far from both sides, you know. How do you define it's far from both sides? So you should define the dots that are closest to the hyperplane. They are called the support vectors, okay? So if you want to define hyperplanes that are far from all the vectors, maybe you just define them as far from the support vectors. Okay, if they're far from the support vector, they are far from the rest of the vectors, right? So you take the closest one. If they are far from the closest one, they are far from everyone. So that's the basic idea of support vector machine. Easy, huh? But then you realize the parameterization has a problem. Okay, why the parameterization has a problem? Because if you want to define the support vectors, okay, then this is the distance between a vector to a hyperplane. Okay, I have an exercise for this week. I'll let you prove it. You know, why is the distance between a vector and a hyperplane this? Okay, many of you still remember, some of you forget. But if you draw a perpendicular line, find the projection of the dot, okay, on the hyperplane, you can find the dot on the hyperplane that is the projection of the dot, okay? And you just calculate the distance between the projection and the dot itself, right? And that's the distance between a dot and a hyperplane. It's in this equation, all right? So the training goal of support vector machine is to maximize this distance between support vectors and your hyperplane, okay? And let's come back to the issue. Okay, when you minimize this thing, you realize, wow, my parameters are redundant. Why are they redundant? Okay, you said wx plus b, right, equals 0 is the hyperplane, right? But no, 2w times x plus 2b is also the same hyperplane. Well, you have some redundancy. You have some redundancy. Then you need to remove one model parameter to make sure that a set of model parameters correspond to a hyperplane. Okay? Which one do you remove? Say you remove b, maybe not a good idea. Okay? You still want to shift it. So SVM does some clever thing in its parameterization. It says, I want to remove a free parameter, right? By assuming, okay? By assuming that this equation is true for all the support vectors, okay? Okay, I remove the free parameter by adding a constraint. That's feasible, right? I just assume that all the support vectors, WV plus B equal 1, okay? And that's a constraint. That equals to the removal of one free parameter, right? So given that constraint, your training objective will be, okay, you minimize the support vector distance to the hyperplane, right? And because the numerator is 1, so you minimize 1 over omega, you know? And that's very simple. They do this removal of free parameter because they want to simplify the training objective. And that's SVM. I think I just took a very brief review of it. So if you want to minimize, if you want to maximize 1 over the norm, it's similar to minimizing the norm squares. Why is there a 2? Because you want the hyperplane to be equal distance to both sides, right? So one side is one distance, the other side the same distance. Okay, let's have a 2. It doesn't matter, right? So you want to find a half, minimize a half of omega norm squared, given a constraint. What's the constraint? The constraint is that your hyperplane can separate those dots, right? Which means that on one side of the dot, when the class label is positive, say y is +1, you assume that, right? So all these dots are WV plus B greater than 1 because the support vectors has 1, so all the other vectors are further from the hyperplane. It must be greater than 1. For all the negative things, then Wx plus B must be smaller than -1 because the support vectors is 1, right? So the other is further from the hyperplane. Okay, so this is SVM. A quick review. So this is the training objective. So can we use our calculus knowledge and to find the best model parameters given a set of data? Okay, unfortunately you can't, right? Because there's no analytical solution, right? When you're given a lot of dots, right? It depends on the dots, first of all, right? And the second, how do you minimize this distance is complicated because it's in a high dimensional space. So we will talk about how to train SVM next week, okay? But let's just do the concept. So we learned the parameterization, we learned the training objective for SVM. Okay, rather than say learned, we reviewed. Okay, we reviewed. Maybe my perspective is different from your machine learning class, but we reviewed SVM. So during testing, what do we do? During testing, we just want to say, given a test sample, right? So we just want to say, is it on this side of the hyperplane or the other side? Okay. So which means is Wx plus B greater than 0 or smaller than 0? Okay. If greater than 0, then it's one type of document. If it's smaller than 0, it's another type of document, right? That's binary classification, right? SVM is built for binary classification. So now let's look at the perceptron. So this is also what you have learned in machine learning. So I go through it briefly. So perceptron has the same parameterization as the SVM. The goal is we are given a document representation V of X, okay, representation, and we want to find a hyperplane. Okay, but basically we want to find omega V plus B, right? If it is greater than 0, it's of class +1. If it is less than 0, it's of class -1. Binary classification. We can understand this parameterization in a vector space theme. Okay, and the perceptron doesn't really specify a training objective, but it specifies the training process. Perceptron is an online learning algorithm. By online learning, I mean it initializes the parameters randomly or to all zeros, and then it goes through all the training instances one by one to update its parameters. This is called online learning. Okay, my training sets are these vectors. I look at the first one, I look at the second one, I look at the third one, okay, one by one, iteratively. Maybe I go through all the training data for several iterations, okay? And then for every training instance, what do? I will adjust my parameters according to whether the current model classifies my training instance correctly, okay? So basically, as you can see from this pseudocode, if the model classifies the training instance correctly, I will just move on to the next instance, okay? But if the model does the prediction incorrect, then I will check whether the gold annotation is the positive class or negative class, okay? If it's a positive class, then what do? I add the vector, right? I add the vector representation of my document into the model parameter omega. And I add 1 to B, you know. So, but if the document is a negative class, what do? I subtract the document representation from my omega, right? And I subtract 1 from B. Okay, this is the update. So I do this, okay, for all the instances. If correct, I move on. If incorrect, I do the update as I just described. Okay, I do this over the whole training set for a few iterations, and I'm done, okay? And the final model parameters are used for classification, just like SVM. Why does it work, you say? It's just a random algorithm. Why does it work? I give you 2 intuitions. Okay, so this is a picture, okay? Suppose you have one positive training example here, okay? It's a blue arrow, it's positive training example, right? And suppose originally the separating hyperplane is here, you know? It does the prediction incorrectly, you know, if it's on the below the hyperplane, it's predicted as negative, right? Okay, if the positive one is predicted as negative, then what do? You add this vector to your model parameter, right? So how do you do? So this, you know, the norm vector is your original model parameter, right? You add this vector to the model parameter. Basically, you tilt it, you add it to it, you tilt it this direction, right? So the hyperplane will be tilted this way, right? There's more chance for it to be above the hyperplane now, okay? Similarly, you add 1 to B. What did you do? So add 1B shifts the hyperplane downward, right? You shift it downward. So more likely the instance will be above the hyperplane. Okay, so that's the intuition. But you can also prove it arithmetically. So basically, you think about the original score is omega V plus B, right? The original score is omega V plus B. And what is the new score? The new score is omega plus V transpose V plus B plus 1, right? So it's like this, right? So what is it equal to? It is equal to omega plus V, okay, plus V transpose V plus B plus 1, right? Okay, it's equal to omega plus V plus B, okay, plus V transpose V plus 1, right? So this is the original score. This is the score after the model update, right? Parameter update. And so the new score is the old score plus the V norm square plus 1, right? So this is above 0, this is above 0. So the new score must be higher than the original score. So it's more likely to be positive. So you can prove, okay? After you update the model parameter, a positive class is more likely to be positive, okay? So it's online update. Is there a deeper, okay, I only showed you, so for one instance it's correct, right? I didn't show you for all the instances. If you do the same, then overall it will find the correct separating hyperplane. I will show you next week, okay? A global view of perception. But now let's move on to multi-class classification. So in nature, so the perceptron and the support vector machines are binary classifiers. So how do you make them to do multi-class classification? Well, there are some ad hoc strategies. For example, you can train a lot of binary classifiers. You want to do three-way classification. And this is called the one versus the rest. Okay, so maybe you'll find a binary classifier to identify class 1 versus the other two classes. And you train another classifier to identify class 2. Okay, and then sort of you merge the results of all these classifiers to make a decision. But this is very ad hoc. What I want to describe to you is maybe you just use one SVM or perceptron, one model, to do three-way classification. Okay, can you? Then you ask me the question, can you use one hyperplane to cut the vector space into 3 parts? Well, the answer is no, right? So if you think about it, of course, one hyperplane only separates the vector space into 2 parts. Then what can you do? What can you do? All right, if I can't change the hyperplane, why don't we change the vector space? That's the idea. No matter whether it's two-way classification or three-way classification, there are 2 types of vectors. What do I mean? If you take both the input and the output into consideration, then there are 2 types of outputs. One type is called correct output. The other type of output is called incorrect output. Okay. Let me show you this picture, right? So suppose you have 2 inputs. One is the star, one is the circle. Okay. One is the star, one is the circle. And imagine that there are 3 classes, C1, C2, and C3. Okay. And let's suppose that in your training data, the star is labeled C1 and the circle is labeled C2. Okay. All right. Then if you consider both the input and output, let's change the vector space. Let's represent the input-output pair into the vector space. Then you can make a difference. Why? Because star C2 and star C3 are negative instances, right? And circle C1 and circle C3 are negative instances. You want to differentiate star C1 from star C2 and star C3. All right. You can use one hyperplane to cut the space into correct outputs and incorrect outputs, no matter how many class labels there are, right? And in this spirit, let us redefine. We have to change the representation. Now, originally we have Vx, right? Now we need to represent the whole thing with Vx and C. How do you turn a document and the class label into a vector? You know, the document vector is like W1, W2 until WV, right? All the vocabulary words. It's a vocabulary size vector. Now, if you want to also put C into consideration, then what do? You do a Cartesian product. What do I mean by Cartesian product? So you compose this V vector with all possible C's. You extend the vector by multiplying it C times. Okay, C is the size of the class labels, right? So you extend it into this thing. It has C rows. The first row is the composition of every word with C1. The second row is the composition of every word with C2, okay, etc. Last row is a composition with the last class label. If you have this long vector, then you have the representation power to represent the composition of every document and every class label. What do I mean? Well, let's suppose we have 2 classes, okay? So work and leisure. And suppose I have a document, Tim went to Amsterdam to meet Jason, okay? then you already know how to do the word vector, okay? So just count the words, all right? And you fill a word vector. Then suppose that the gold label of this document is work rather than leisure, okay? Then what do? You fill this word-based vector into the work row, of the high dimensional vector, okay? The leisure row will be all zeros, because the document is tagged as work, right? So the work row will have team, work, etc. So etc. non-zeros. So basically, you compose the word and the class label, right? And every feature in the vector is a composition of word and class label. And in this way, you can map an input and an output to a distinct vector. Okay? So the row that corresponds to the output has non-zero values. And like elements with the word has non-zero values. That's easy. So the Cartesian product. So basically the composition of all possible words and all possible class labels. And now let's move on to SVM. Then we can do the same, right? So we want to say, remember, this is like things above the hyperplane are correct samples. Things underneath the hyperplane are incorrect samples. So all I need to do is to replace VD, the representation of a document in support vector machine, into V of D, C, the input-output vector. And then I can do the same with a support vector machine, right? But it turns out that this model is a little bit redundant. It sort of is too strict. Why is it too strict? Because during testing, right, I still have an input, right? I want to do what? I want to combine this input with all possible outputs, right? C1, C2, and C3, right? I want to find input and C1, is it above the hyperplane? Input and C2, is it above the hyperplane? I'm assuming that only one of the output, right, is above the hyperplane. But in testing, that might be not true, right? Maybe all of them are above the hyperplane. Maybe all of them are below the hyperplane. I don't have any control, right? But what I can do is I can choose the one that is the furthest up to the hyperplane, Which means I can choose the one where omega VDC plus B is the highest value, right? All right. Then you say, this is like a week 2 now. Okay? So for all the things we've been discussing this week, we're playing with vectors in a hyperspace. But now we come back to, no, you are scoring things, right? So you're given an input. You try to score the input with all possible outputs. And you try to find the highest scored one, the one furthest from the hyperplane as the output, right? Oh, this is like week 2, and this is like week 3 now. So if this is true, okay, when we train the model, do we still need to make sure that all correct examples are above the hyperplane and all incorrect samples are below the hyperplane, right? Isn't this too strict? Can't we just simplify the training objective accordingly, okay, to say, as long as my correct training samples are scored, okay, at least 2 or at least 1 above my incorrect samples, then I'm satisfied, right? All right, so I can change SVM a little bit to say, for all these training data, okay, originally I want to make sure that the correct class labels are scored above 1, right? Incorrect class labels are scored below -1. Now let's change it a little bit. Let's change it to, we score it such that the correct one score minus the incorrect one score is greater or equal to 1. That can already separate this data, right? Okay, I don't really care now. I don't really care where they are to my hyperplane, I only care about their relative positions, So because of that, because I only care about the score difference, I can reparameterize my SVM a little bit. I don't care about the distance of the support vectors anymore, right? I don't need B anymore. Let's just say I only need omega, okay? Because omega Ci minus omega C, the B and B, they cancel each other, right? They are no longer useful in my model. So my model parameterization also changed, right? So in the end, I only care about omega VDC. That's my model score, okay? And my training is to make sure that the correct one is stronger than the incorrect one. My testing is to say, given VDC, I want to find the one that has the highest omega times VDC. All right. So that's my new formula of multi-class SVM. All right. Okay, so multi-class perceptron. You know, perceptron, it has the same parameterization as SVM. So let's specify it out. So the modeling target, okay, is to score class labels, okay? How do you score class labels? I score class labels by first representing the input and output into a vector, V, D, and C, okay? All right. And then the way I calculate my score is to use a model parameter omega of the same size to dot product my VDC. That's my score. All right. So this is the model. And how, during testing, what I do? During testing, I just find argmax C, the score. What does argmax mean? Okay, I've shown you argmax a few times. Argmax, it means I find the argument, okay, namely C, that maximizes the equation, namely the score of D and C. This is argmax, okay. If I change it to max, what do I mean? I mean, I find the maximum value of the score. That's called max. Argmax means I find the argument that gives the maximum value. All right. So this is testing, and how do I train the model? The training is a slight change of the binary perceptron. The thinking is the same. I still randomly initialize my model parameter omega, okay? Or I initialize it to all zeros. And then I do an iterative training process. So basically, I take my current model, and I use the model to go through all the training instances for multiple iterations, okay? I scan through all of you, one iteration. Scan through all of you, second iteration. And in each iteration, for everyone, for every training instance, I compare my model output to the gold standard label, right? Because all my training instances are labeled. And I update my model parameters if the model output is incorrect, okay? So how do I update my model? Okay, so I first find the output class. I call it Z, okay? For the input Xi, I calculate my model output class label Zi, right? And I compare this Zi label with the gold label Ci, okay? The class Ci. Now, if the output is correct, I move on to the next instance. I'm fine, right? I did it correctly. If the output is incorrect, what do? I just add the representation of Ci, namely VDCi, to my omega. They're the same dimension. And I subtract the representation of my Zi, okay, VDZi, from my omega. Okay? So, and that's it, right? So if I'm correct, I move on to the next person. If I'm incorrect, I take the gold feature vector representation, I add the gold vector representation to my omega, and I subtract the model output representation from my omega, and that's it. Okay? So that's the perceptron. And after I go through my training instances for several times, I stop. And the model is there. Why is it correct? Again, I can give you one intuition. The intuition is very similar to what I did here, okay? I just leave you to watch the slides. So originally is W transpose V, right? Originally is W transpose V. But V, D, C, VDC. But this W transpose VDC turns out to be smaller than W transpose VDZ. Z is your model output, right? So that's why you selected your model output. Now you update your model by the new omega will become omega plus VDC minus VDZ, right? So this is your new omega, all right? So you can prove that by using the new omega, the score difference will be smaller. This has a higher chance than that one, okay? So that's what's shown in the slide, right? And you can prove it yourself. But why does it work globally? We will see that next week. But now let's, after we reviewed, okay, binary SVM and multi-class SVM, binary perceptron, multi-class perceptron, let's move on to features. All right, I want to unify naive Bayes and SVM and perceptron, okay? And I want to show their difference. So the first difference between them is, okay, how about let's first see the similarity. I've already indicated the similarity, right? For every word, you have a parameter, okay? The parameter indicates the class label of the word, right? So the parameter for perceptron and the SVM is omega. The parameter for naive Bayes is log PW given C, right? So they serve similar things. But the difference is that naive Bayes does classification by, making a generative process, right? So you generate the document and the C by first generating C, and then you generate every word in D. That's called a generative model, right? The perceptron and SVM does different things. I just directly, brute forcely, or straightforwardly score different C, right? I don't say I'm not a probability model. I didn't generate word and class. I'm given a set of words, right? And I find the representation of this set of words with a class label. And I try to score every class label to differentiate correct and incorrect samples. And this kind of model is called discriminative model, not generative model. It differentiates samples, okay, but not generate a sample. So this is the first difference. All right. And what's the advantage of discriminative model? All right. So, okay. So before I tell you the advantage of discriminative model, let's first unify all the three models. So the first thing, let's look at the naive Bayes again, okay? It's a linear model. It's very similar to perceptron and SVM. So basically, you have a document representation. You have a model parameter vector. You make the dot product, right? So this is exactly the same as perceptron for binary classification. But wait, so naive Bayes has another parameter called log PC, right? The perceptron doesn't have it. Log PC says if a sports document is much more than finance document, then you will have a higher probability to sports document. That's a useful pattern, right? That's useful to have. Can you add that to the perceptron? It turns out that you can treat the representation of a document as this. You add a 1 to the vector, okay? So in addition to the count of every word in the document, you add 1 as the first element in your document representation. And then you change the vector of your parameters by putting log PC into the top, okay? And if you do this, you simply do the dot product, it's still the naive Bayes model, right? So this gives us a hint. This gives a hint. We can do the same by extending my representation vector for perceptron. How do I do that? Okay, so I can extend my VDC representation by adding 1 row. Okay, the number of C1, the number of C2, until the number of CC in my representation. Basically, I added some elements, right? So how does this work? So when the class, okay, of the DC pair is C1, then in the first row, only the C1 is 1, right? The remaining is 0. Okay? So if DCC is C2, then only C2 is 1, the remaining is 0. So this provides information about C itself. Then in my perceptron model parameter, you know, I will have an element that corresponds to this row, each element in the row, okay? And then when I train the perceptron, this element will have a value, right, a weight. This parameter will have a value. The higher the value, it means the more likely this class is because it's scored higher, right? Right. So similarly, the model parameter linear dot product, right, will have a score on every word and class association. And those scores correspond to log PC. All right. All right. So in that spirit, you know, we can put a naive Bayes. This is the naive Bayes model. I write it here. Okay. I can spell out that the naive Bayes model is basically exactly the same as the perceptron and SVM for multi-class classification, because this is the vector representation of my document and my class label, right? This is all the model parameters for naive Bayes. I just arrange them in this order, you know? Log PC1, log PC2 until log PCC, right? And log PW1C1, log PW2C1 until log PWVC1, right? And log PW1 given CC, log PW2 given CC, etc., right? The last word and CC. So I'm claiming that if you dot product this representation vector with the naive Bayes parameters, you get this equation. Do you agree with me? Yeah, many of you agree, right? So if you train this, okay, by counting relative frequencies, you get a naive Bayes model, right? But if you train this vector by perceptron, you get a perceptron, right? If you train this by using SVM, you get an SVM. The representation is the same, right? So that's what I want to tell you for this week. But I promise you I will tell you a difference between generative models and discriminative models, right? What's the difference? The difference is that, okay, for naive Bayes, you have no way to change your representation vector. Your representation must correspond to your feature vector. Not feature, sorry, I didn't introduce feature to you. It must correspond to your parameter vector, right? This is the parameter vector. Because naive Bayes is a generative story. It first generates the class label and then generates every word. So your model parameters are like this. So your representation must correspond to your model parameters. You can't change it. Okay? So this is the generative model. You can't generate something twice, right? But for perceptual and SVM, well, it's a discriminative model. You define the representation yourself, whatever you like, right? Originally, we defined it only with the word rows. Now I define it with the word class rows, right? Can I change it further? The advantage of discriminative model is that you can change your representation as long as you like. Okay? So how can I change my representation? So you know we learned bigrams, right? Last week we learned bigrams. So if I tell you, okay, if I tell you that your document contains the word world, okay, what is this document? Is it news, financial news, or sport news? You don't know, right? If I tell you the word cup, okay, is this technique news or sport? I don't know. But if I tell you World Cup, it's sport news, right? This is a bigram. So bigrams can be stronger features than unigrams, right? Okay. So naive Bayes cannot integrate bigram patterns, right? Okay. So similar, if I tell you return, if I tell you abnormal, you don't know what it is. But if I put them together, abnormal return, this is finance news, okay? All right, so how do you add bigram features? It's easy. You just extend your representation vector to be longer, right? You attach all possible bigrams to the end of your vector. Your vector is much longer, right? All possible bigrams. And then given a document, you just count, okay, which bigrams are in my document and fill the elements in the vector, okay? Just like you fill the word elements, right? So your vector now has class label, right? Has word and class label composition. Now it also has bigram and class label composition. The vector will look like this. Okay? You added a few rows to your vector representation, right? Every row is the set of bigrams combined with a class label. So when you have a class 1 and a document, all right, which elements are non-zeros? In the first row, class 1 is non-zero, okay? And then among the word rows, only the class 1 row is non-zero. Among the bigram rows, only the class 1 row is a non-zero. The remaining are zeros. So this is your new representation. With that, I can tell you what is a feature. So basically, a feature is just an element in your vector, you know. Every element is a feature in the vector representation. And the vector is called a feature vector, okay? So the feature is just a pattern, okay? But just like, so feature is on the representation side. The parameters are on the model side, right? They're different. They're different. So, but similar to model parameter types and model parameter instances, you have feature types and feature instances, okay? And the feature types are also called feature templates. So when you have W and the C composition, it's a type of feature, a word and a class, right? So this is called the feature template. And the feature instances are what? The word JSON and the word and the class label work combined together. This is a feature instance, okay? You define a feature representation vector by specifying feature types or feature templates. And for that, we specified class label C as a feature template. The composition of word and the class label W and C as a feature type, okay? The composition of binary bigram and the class type BI and C as a feature type, okay? There are 3 feature types. How many instances? Cartesian product, C plus V times C plus BI C, this many instances. So this is the feature vector. All right. So, and all our linear models can be represented as feature vector phi, okay? And a model parameter vector theta. And the parameterization is like theta dot phi is the score, right? Now, this is the same as what I did for week 2, right? All right. So I introduced the story to you so far, and we arrived at what I discussed earlier. That's a linear model. Okay, so features are very important to linear models. You know, if you look at NLP papers in 1990s, 2000, a lot of papers are about feature engineering. What is feature engineering? You just tweak with the feature templates. When you tweak the feature templates, you change the representation vector space, right? When you change the vector representation space, you can do magical things, right? What can you do? This is about some machine learning theory. So, well, if you have a low dimensional space, if your features are not very expressive, then you know your training instances might not be linearly separable, right? So when you increase the features, bigrams, trigrams, fourgrams, all different kinds of features, then the dimensionality of your space is big. It's very easy to find a hyperplane to separate training instances, right? So the richer the features, the more powerful your model is, but does it mean that I can just throw all possible features in my model? I got a super model. It's not that simple. Okay, so there are two concepts in machine learning. One is called separability. I already introduced that to you, right? So if your training data are separable by a hyperplane, it's a linearly separable, right? So we will build models that are more powerful than hyperplanes later. Okay, so if you increase your features, if you increase the dimensionalities, you know, you can find a hyperplane to separate your training data. Okay, so your training data can be perfectly separated. All right, this is called separability or model fitting. If your representation on the left-hand side is expressive, then you can build a powerful model to fit your training data. But in the extreme case, okay, your features can include the whole training documents. Can you? Remember last week we did that, right? We treat the whole input document as features, right? In the end, you easily separate your training documents. But then the model did what? It only remembers your training data. It cannot be used to differentiate your test instances, right? All right, so there's a trade-off. If your feature is more expressive, your training data, you can easily fit your training data, but you might not generalize well. You know, given unknown data, your model might not perform as well. This is called overfitting. You fit your training data too well, you cannot generalize. On the other hand, okay, if your feature representation is not expressive, you cannot fit all your training points. This is called underfitting, all right? So now you'll understand why do people do feature engineering, right? You want neither overfitting nor underfitting, so you want to tweak your features, okay, to suit your model. All right. Okay, so if you tweak your features and your training data is not that linearly separable, can you still train SVMs? So that's my last topic. Okay, my last topic. So it's like this. So if your training data cannot be separated by a hyperplane, then can you still specify an SVM? Okay. So we can change it a little bit. We can say, originally I require, okay, let's say the binary case, I require all positive examples to be at least 1 above the hyperplane, all negative examples to be at least the -1 below the hyperplane. So if I say y is +1 or -1, I say y dot the score must be greater or equal to 1, right? But if you cannot separate your training samples, this constraint cannot be satisfied, okay? Then for some training samples, the y dot the score can be lower than 1. Okay, now why don't we just say, for all the training samples, I want to make sure that y dot the score is equal to 1 minus a slack variable. Or actually, I should say it's greater or equal to 1 minus a slack variable. Okay? If the dot sits between 1 and the hyperplane, the slack variable is between 0 and 1. Okay? If the dot falls on the other side of a hyperplane, then the slack variable is above 1, you know. 1 minus this thing is negative, right? So it's on the wrong side. Okay, so the slack variable, okay, but if y dot this score is greater than 1, you know, the slack variable can be 0, okay? So there's no violation. So the slack variable defines the violation. Okay, so I can summarize my slack variable as this thing. Max 0 and 1 minus y dot the score, okay? So that summarizes what I just told you. So if y dot the score is greater than 1, then the slack variable is 0, no violation. If 1 minus y dot the score is more than 0, then there's a problem, right? So that's a slack variable. So if I define the slack variable as this, max 0, y dot the score, then I can say, okay, I want to minimize the 1 over, I want to minimize the W norm, okay? I want to maximize 1 over W norm. And I want to minimize the slack variable as well, okay? So for all training instances, each training instance has a slack variable, has a violation. All right, if I want to minimize the two things, I no longer have constraints, you know, because the constraint is already expressed in my slack variables. So in the end, I only need to minimize this thing, the sum of all slack variables plus W norm. That's my new objective, right? So I want to minimize the violation to the score plus my original score margin. Okay, so that's a new training object. But I want to weigh the two things. Maybe you think the violation is more important. Maybe you think the original margin is more important. So I add a constant C, okay? So you minimize C times the total slack variable plus the W norm squared, okay? All right, you can ignore about the half, it doesn't really matter. Okay, so this is the new training objective. It becomes an unconstrained minimization problem, right? Unconstrained minimization. So similarly, for multi-class SVM, we can do the same. Originally, I want the correct samples to be scored higher than incorrect samples by at least 1, right? Now I don't do that. I say I want the correct samples to be scored higher than incorrect samples by at least 1 minus the slack variable. Okay? For every training instance, there's a slack variable. Okay? So if the score difference is more than 1, I can say the slack variable is 0, no violation. But if the score difference is smaller than 1, then my slack variable is 1 minus the score difference, right? Okay, so as a result, I can specify my training objective like this. I want to minimize the original training objective, the parameter norm, okay, plus C, the hyperparameter weight, times the sum of all training data, the slack variable value. The slack variable value is the maximum of 0 and 1 minus the score difference. Okay. But why is there a second max in the equation? Why is there a second max in the equation? This max is the model output. You know, because the model finds, okay, the highest scored class label as the output, right? So max C omega phi xc is the model output, okay? And so the score difference is the gold sample score minus the model output score. I want 1 minus this thing, okay, to be the slack variable, okay? If 1 minus this thing is smaller than 0, then we're fine, no violation. So max 0 on this thing. If this thing is more than 0, then we have a violation. We want to minimize it. So this is the total violation thing. So this is the original training objective. Okay? All right, so this is the new view of SVM objective. Okay? New view of SVM objective with slack variables. So, you know, after I introduce the slack variables, for both binary classification and for multi-class classification, it becomes an unconstrained minimization problem. No longer constrained minimization. Okay, we will take more look about how to optimize it next week. But how about perceptron? If the training data is not linearly separable, do we need to do something to the perceptron? Okay, we don't need to do anything. The original multi-class perceptron algorithm can still be used to train over non-linearly separable data. Okay, theory shows that this algorithm will converge, okay, to a minimum of training errors. It means that the perceptron can fit the training data. Okay, so no matter whether it's separable or not separable. Okay, we're done. Let's take a brief review of what I did. So all in all, this week we learned feature representations, right? Okay, word-based, word and class-based, word and class and bigram and class-based, and class-based. So, and I showed to you that if you can represent the input or the input and output into a vector space called feature vector, then we can train clustering algorithm. Okay, we can define clustering algorithm and we can define classification algorithms. Okay, and we started with a vector space geometry, but we ended up with a scoring mechanism. Okay, so you should bear in mind both the vectors and the scores. Okay, and I also showed you the importance of your feature definition, the representation, to your model performance. Okay, I showed you overfitting and underfitting. So this is very important. So representation will be a theme of all these terms. Okay, so let's see you next week.